So, dear colleagues, despite of situation in Kharkiv and in Ukraine and bombing of our cities today nights and today day, we started our Kharkiv chemical seminar, and it's pleasure to introduce our speaker, Professor Daniel Werz, who currently holds the chair of organic chemistry at the Albert Ludwig Universität Freiburg. Professor Wertz's academic career started at the University of Heidelberg, where he earned his PhD degree in 2003. His scholarly trajectory includes distinguished postdoctoral appointments at ETH Zurich, at the University of Heidelberg, as well as tenure track path leading his habilitation at the University of Göttingen. Prior to his current appointment in Freiburg, he served as a full professor at the Technische Universität Braunschweig. The impact of Professor Wertz's research is evidenced by his extensive publication record, comprising over 270 international recognized articles. His work has attended significant international resonance with more than 16,000 citations. Beyond his research achievements, Professor Werz is a prominent leader within the global scientific community. He currently spearheads the Liebig Association of Organic Chemistry and its chair, and serves as a scout of Alexander von Humboldt Foundation, very famous foundation also for Ukrainian scientists. And please join me in welcoming Professor Daniel Werz for his lecture. And Daniel, floor is yours, please.
Valentin, thank you very much for this very kind introduction. Yeah, and I very much appreciate that you listen even under these circumstances to my lecture. So we heard in Europe here in Germany there should be a ceasefire, but as I heard, well, this is not true at all. It's so horrible that this war is now lasting for about 4 years. Well, I hope that at least for the next hour, everything will be more or less quiet and you will hopefully enjoy some chemistry. So I would talk about strain systems today. Donor-Acceptor cyclopropanes to access carbo and heterocyclic compounds is the title of this talk. So you all know cyclopropanes. These are the smallest carbocyclic ring systems. And well, if you ask yourself, what can you do with cyclopropanes? The question is, well, what kind of chemistry? The normal cyclopropane you just can burn, right? There's not much to do. This is a bit boring. But the situation changes completely if you put donors and acceptors at adjacent positions at the three-membered ring, as you've seen it here. I hope you see my cursor, right? And if you do this, you can write a 1,3 Swidder ionic relationship where the positive charge is stabilized by the donor and the negative charge is stabilized by the acceptor. And taking this into account, you can think about different classes of reactions. For example, ring opening reactions with a polarized system XY, and you end up with bisfunctionalized open chain systems like this here. Or you can think about cycloaddition reactions in which you insert 1 or 2 or 3 or 4 atoms to get 4 or 5 or 6 or 7-membered ring systems. And if you consider that this negative charge can be also delocalized at the accepting moiety, and I've written the accepting moiety here a bit differently, then you might think that also another atom of this moiety might attack this positive charge, and you end up with a ring enlarged structure, as you see it here on the right side. Well, essentially, this chemistry was invented by Ernest Wenkert, an American chemist, and Hans-Ulrich Reissig, a German chemist, more than 40 years ago. And they did some work, but then, as usual, well, not a lot happens. And it was about 15 to 17 years ago when some more people, and also our group, started again to work in this area. And here you see some names, more or less famous, of people and groups who contributed. but I think we also contributed a bit. Well, before I start with my own work, I would like to show you 3 examples. One, a very old one, more than 40 years old, by Hans-Ulrich Reissig. He said, okay, I take a donor-acceptor cyclopropane with a silylated alcohol as a donor. And the accepting moiety is an ester, as you see it here. But an ester is not really a great acceptor. But he said, okay, next to this ester group, there is an acidic proton. I use LDA to deprotonate. Then I take carbon disulfide and methylate. So I get another accepting moiety. And under the influence of Brønsted acid, the system rearranged. And after elimination of TMS alcohol, you end up with this thiophene-like structure. Well, maybe even more easy to understand is the chemistry by Jeffrey Johnson, an American chemist. He said, okay, I take 2 acceptor moieties here and an error unit as a donor. And this is the weak bond. And under the influence of magnesium 2+, I insert this aldehyde and I end up with highly substituted tetrahydrofurands. And my Swiss friend Jerome Vaza at Lausanne, he said, okay, I want to use this chemistry for natural product synthesis. This is the weak bond, nitrogen as a donor, a keto group as an acceptor, and under the influence of Brønsted acid, the system rearranged. Now another donor atom attacked here, and he ended up with this aminal-like structure being an intermediate in a natural product synthesis. Well, when we started in this area already a long time ago, we had some fun with these structures you see on the top. Oligocyclic oligoacetals or anylated THF moieties. And the working hypothesis we had at that time was very, very simple. Can we access these structures by donor-acceptor cyclopropane chemistry? And the idea we had was very simple. So we said, okay, furane is the least aromatic of these 5-membered heteroaromatic compounds. It can be cyclopropanated to get this. Well, we have to adjust the oxygen functionality here to get a really perfect acceptor. But now you have a donor and an acceptor, and this should be the weak bond here. So maybe this rearranges very easily to get something like this. And with this, okay, you can continue to get the larger structures. So Tobias Schneider at that time took this challenge and he used ethyl diazoacetate under kappa catalysis. And he was able to perform a 2-fold cyclopropanation to get this tricyclic structure. And as you already see, oxygen as a donor and ester as an acceptor. But an ester is not really a great acceptor. So this is a stable molecule. We thought we have to convert this into an aldehyde. So we did this via a 2-step synthesis, via alcohol, lithium aluminum hydride as reducing agent, and then we oxidized by IBX, the alcohol to the aldehyde, but the aldehyde, the bis aldehyde, was not able to be isolated. It immediately rearranged to this tricyclic bis acetal. And as you see here, this is the X-ray crystal structure. The 2 5-membered rings are anylated to each other at the central 5-membered ring. You can even do this in an asymmetric fashion. If you use a box ligand in this first step, you get about 93–94% EE. And of course, the chirality you introduce in this first step is then translated also to this tricyclic product. And what is nice now? Well, we have another electron-rich double bond. Before, we also had an electron-rich double bond. So you just can continue. Same chemistry, ethyl diazoacetate, kappa catalysis. Now we end up with this pentacyclic compound, reduction and oxidation, and we get the pentacyclic tetraacetal, as you see here in the middle. And so we continued and continued. I have to confess the yields get worse and worse. This is because these structures are at some point hardly soluble. You see there are not too many hydrogens left, and it's a relatively rigid structure. They all nicely crystallize, and here you see one example, the crystal structure of this final nonacyclic compound. and you see all the 5-membered rings are annihilated in an anti-fashion. And what is also nice, what this crystal structure shows is how such a chemdraw, a 2-dimensional representation, might cheat you. You might think that there is only one 5-membered ring missing here to close the structure, but you see how far these 5-membered rings are apart from each other. Of course, this is because one 5-membered ring goes up, the other down, up, down, up, down. And what must not be underestimated is that carbon-oxygen bonds are much shorter than carbon-carbon bonds. And here at the outer rim, we have only carbon-oxygen bonds. So this is really old chemistry from my group, more than 15 years old. We had some fun at that time, but we wanted to look into this chemistry from a more fundamental point of view. So the student who worked at that time, had some fun to create such a cartoon where we have an electron donor, a push substituent, and a pull substituent, an electron acceptor. And as you know, of course, there is not only oxygen as a donor and an aldehyde as an acceptor. So we have many, many other donors and many other acceptors, donors such as amines, such as other chalcogens, sulfur, selenium. Even halides might be donors. And at the acceptor side, of course, also nitro groups, amino groups, nitroso groups can be all acceptors. And we wanted to look, first from a theoretical point of view, what might be the most efficient donor-acceptor combinations for this rearrangement process. Here you see a 3-membered ring, which rearranges to a 5-membered ring. And we looked into this chemistry for 72 donor-acceptor combinations. Here you see 8 donors, and here at the acceptor side, there are 9 acceptors. So this is an ester and an acid. So and 8 times 9 is 72. And for all these 72 combinations, we optimize the starting material, we optimize the product, and more importantly, we optimize the transition state. So very simple computations, 1 molecule, no catalyst, concerted process, no solvent. We just wanted to get a feeling what might be possible. And we know, of course, from our chemistry, from our experiments, that this oxygen donor here, OMe, and an aldehyde acceptor, it's this bar here. This rearrangement worked. And you see here in this range, there are many, many other systems that should rearrange as easily as you've just seen before. I would not go here. This would be a chlorine as a donor and an acid as an acceptor. So this is a really high barrier, 250 kilojoule per mole. Well, not really accessible, right? But here, many, many systems should rearrange as easily as this oxygen donor, aldehyde acceptor. We did not look into all of them. But Johannes Kaschel at that time, PhD student, he said, okay, I want to look into oxygen donors, imine acceptors. And he used again this compound, 1 step from furane, and first converted these ester groups into ketones. And the ketones, we know this is very old chemistry, can be reacted with amines to give imines, Schiff-base chemistry. Well, and to be honest, I thought, okay, then this imine would rearrange to this tricyclic compound, nitrogen, oxygen, nitrogen. Similar to the one we had before with oxygen, oxygen, oxygen. But what I completely underestimated at that time was the power of aromaticity. Well, have a look here. So here you have a dihydropyrrole, right? Before we had a dihydrofurane. What's the difference? Well, the tendency of a dihydropyrrole to become a pyrrole is much higher than the tendency of a dihydrofurane because the aromaticity of pyrrole is much higher. And this possibility is given here. So you just eliminate water, oxygen here, hydrogen here, and you end up with these 3 linked bis pyrroles. So we never wanted to prepare them, but well, it happened. And well, okay, you can also use other diazo agents in the beginning. Then you have, for example, here another residue R3. do the same chemistry, and you end up with a more versatile substitution pattern. You can use not only normal imines, you can also, as you see here on the right side, as amino source to sulfonamides, for example. And you see we get all the time these 3-3-linked bis pyros. Well, so these were rearrangement reactions. What about cycloaddition reactions? I've shown you in the beginning this example by Jeffrey Johnson where the aldehyde was inserted into a donor-acceptor cyclopropane. If you try to do this chemistry with a ketone, this chemistry doesn't work because, well, the ketone might be sterically too bulky or the electrophilicity at the carbon of the ketone is not high enough. So we thought, what about thioketones? Thioketones have a much more nucleophilic heteroatom with a sulfur than ketones. Is this possible to be inserted here to get these highly substituted tetrahydrothiophene? And of course, you have to do optimization. I don't want to bore you with that. It turned out that aluminum trichloride, just 10 mole % in dichloromethane at room temperature, easily allows an insertion of this benzothiophenone to get these 5-membered ring compounds. And here in blue, you always see the donor. It works with aryl bonds, but also it works with vinyl groups, just a double bond. Even with an aliphatic group, in this case, it worked. You see heteroatom substituted. You see heteroaromatic compounds like this thionyl residue, and even here a nitrogen as a donor in form of an imide. So then we said, what about putting these two reactive functionalities into one molecule? So put at one terminus a donor-acceptor cyclopropane, and at the other terminus a ketone. And then we use Lavesson's reagent. This is this thioketonation reagent, transforming a ketone into thioketone. And, well, maybe they should react with each other and lead to interesting bi-tricyclic structures. Well, indeed, we added a little bit of aluminum trichloride, and we got these tricyclic structures, as you see here. Well, this red part is always from the thioketone or thioaldehyde. In this case, it's a thioaldehyde. And this part here is always from the 3-membered ring. And you see you get bridged sulfur over a 7-membered ring, or also bridged sulfur over an 8-membered ring. And here at the right, you see an X-ray crystal structure, the bridging sulfur, the 2 ester moieties. These 3 carbons here are from the cyclopropane. Well, if you have looked into recent literature, last 2-3 years, you see all the time bicyclobutanes. What are bicyclobutanes? And you see great papers in Angewandte and JACS, bicyclobutane chemistry. So to be honest, bicyclobutanes were prepared for the first time a long, long time ago. And here you see a bicyclobutane. And we had in mind in my group also to use bicyclobutanes maybe 7-8 years ago. But then I said, well, why should we do this? The people will just tell us, okay, this is an even more strained donor-acceptor cyclopropane because there's another 3-membered ring, right? Okay, I was wrong. We should have done this much earlier because then many people, especially from India and China, but also Germans and Americans, came into this play and had great papers. And yeah, we did not realize that there is such a hype for a long time. And at some point I said, okay, let's also do some chemistry with bicyclobutanes. And you've seen our chemistry with the thioketones. And we thought, okay, maybe we can just transfer this chemistry into bicyclobutane chemistry, because then you have here this further bridge. Yeah, this is all the summarized under escape from flatland. And we tried to use our common conditions. Yes, it worked, but then we figured out that because this is even more than 60 kilocal per mole more strained. It's about 60 kilocalorie per mole strain in contrast to about 27 of the cyclopropane. So more than double the strain. That with these huge strain, You don't need any catalyst anymore to activate further. You don't need light. So often also light is used to activate a reagent. No, you can do this. You just put these two compounds together and immediately you get this scaffold, which was, by the way, not known before. Sometimes you really wonder that there are very simple scaffolds with the sulfur here, which are not known before. Okay, and here you see again in green the donor parts. Also aliphatic donors work. Here in blue, different acceptors. And it's so reactive now that you even don't need the donor anymore. Even a hydrogen, as these two last examples show, allow this reaction. Here in the last one, we got the spirocyclic compound. This was just cyclopropene thione, which was inserted. Okay, coming back to the common thioketone insertion. So if you look in the periodic table under sulfur, there's selenium. And well, then the question was in my group, are there selenoketones? Oh yeah, there are selenoketones. And then the question is, oh, how do you prepare a selenoketone? To prepare a selenoketone is very, very simple. I was really amazed that it's so simple. You just take the diazo compound. Here, where the selenium is now, N2, diazo compound. And then you take gray selenium powder, you can buy that, and put it to your flask. You can do this under the air. And then you stir it, and then nitrogen bubbles out, because the selenium substitutes the nitrogen, and nitrogen is the gas and comes out. And then here you see a picture at the right side. You take your reaction mixture, and you filter off the excess gray selenium. Here you see it in the funnel. And this green stuff here is your selenoketone. You just concentrate it, no column chromatography, no distillation. You just concentrate it and you use it for your next reaction. And you can easily follow this reaction by optical inspection because, as you might easily understand, this product here is not green anymore. This is slightly yellow. The green color comes from this carbon-selenium double bond, carbon-selenium pi bond character. Okay, here you see the products. Selenium or selenoketones are easily inserted. We also crystallized one. You see this 90-degree angle here at the selenium, as expected. And the conditions are very similar to the thioketone. Yields are a little bit worse. Okay, so what you've seen so far is the generation of 5-membered rings. Thioketones, selenoketones used as a 1,2 dipole. At some point we had the question, or we raised the question, whether also such an ortho-bis thiobenzoquinone can be inserted. You can write this like this with carbon-sulfur double bonds. You can also write it with a benzene structure, and then you have to separate charges, or you would write a sulfur-sulfur bond, but then you have a highly strained 4-membered ring. So nothing is really great. If you look up whether this compound exists, well, you see people have created it and then characterized it in a matrix. Okay, you cannot really use it. But if we would have it, or if we would have something like a surrogate, a compound that liberates it, we would maybe end up with such 7-membered rings. And we did not really have an idea, but then a guy working in a completely different field in my group, not with strain systems, but with palladium, he used for one of his reactions this dicyanato benzene, as you see it here. And the reaction did not work, as it's very often the case. But he had palladium in and triphenylphosphine, the ligand for the palladium. And he was a very smart student. And he said, okay, I look what happened. And he found this compound here shown in the red box, a dithioloimine. Okay, and then he was talking to the people in the strained ring system subgroup, and he said, well, I'm pretty sure you can deprotonate the nitrogen using a base. And then this might open up to a thiolate and a thiocyanate. And the thiocyanate, SCN, has, of course, a positive polarized sulfur. And if you use this compound You just take HCN out and you should get these 7-membered rings. And Leonard Garber then took this challenge and said, okay, I try to optimize this reaction. I try to realize the reaction and try to optimize it. And finally, he figured out, okay, we need a Lewis acid to further activate this bond. And a bit unusual one, titanium tetrafluoride was the best. Also works with other, but titanium tetrafluoride works the best. And of course, you need a base to deprotonate here. And Lewis acid and Lewis base have to be compatible with each other. It's not possible that they kill each other. Then you don't have reactivity. So you just take HCN out and you get these 7-membered rings, as you see here at 8 examples. What was a nice spot-to-spot reaction. And then, he came 2 days later to my office and said, have a look. This is the NMR spectrum. And I tell you, the NMR spectrum looked horrible. I said, but that's strange. It was such a nice reaction. And also the mass is correct. The mass shows the mass of these 7-membered rings. And indeed, then he was able to crystallize the compound. And also the crystal structure was fine. Here you see 2 sulfur, 7-membered ring. Yeah, and then we figured out, well, at room temperature, these 7-membered ring compounds with 2 endocyclic heteroatoms and an anylated benzene, they exist in several different conformations. And these conformations are separated by high activation barriers. So at room temperature, they do not interconvert in each other. This means in your NMR spectrum, you have the mixture of 2, 3, 4 compounds. And therefore, the spectrum looked horrible. So then we heated up to 70 degrees and we got perfect spectra. So sometimes this is the solution if you have bad spectra, but not very often. Okay, what about 4-membered rings? You've seen 7-membered rings, 5-membered rings. What about 4-membered rings? Can we just insert 1 sulfur into a donor-acceptor cyclopropane? We were very naive and said, okay, let's take the cyclopropane, a Lewis acid, toluene, because sulfur is soluble in toluene. And then we put elemental sulfur there and boiled it. Nothing happened, of course. So then we thought a bit more seriously about that. What about a nucleophilic sulfur source? Thiocyanate, SCN-. Of course, nucleophilic in sulfur. So we tried that, and ytterbium triflate is a catalyst, but we ended not up with a 4-membered ring. We ended up with a 5-membered ring. So this thiocyanate attacked this carbon here, and then the emerging malonate attacked the carbon in the CN. And this led to this amino group, and 1 ester is eliminated. So if you're interested in dihydroaminothiophene, this might be the method of choice. But okay, this is not what we wanted. So then we thought again, we need a sulfur source which is nucleophilic, but which has a leaving group that cannot be attacked by the emerging malonate. What about this? Thiosulfonate. And with this one, we were indeed able to create 4-membered rings. But you see, the yields are poor. Never more than 25%. So we got another major product. And after optimization, this major product was this 5-membered ring with 2 sulfur. We use this salt here, thiosulfonate, nickel bromide to activate, and we get the insertion of 2 sulfur. Here you see an X-ray crystal structure, 2 sulfur atoms in this 5-membered ring. Okay, so we looked a little bit into the mechanism. And here you see, okay, we have the nickel bromide to activate. The bond gets weakened. Then the thiosulfonate comes into play, attacks the 3-membered ring, and we have evidence that this is an intermediate because after protonation, we can isolate this ring open structure. Here you see SO2, sulfur, and here are the 3 carbons of the 3-membered ring. Well, our idea was that this negative charge attacks the sulfur, and sulfinate is the leaving group. And we get a 4-membered ring. But of course, such a 4-membered ring would build up a lot of ring strain. But we still have a lot of thiosulfonate around. So the thiosulfonate attacks probably this sulfur, kicks out the sulfinate, and forms a sulfur-sulfur bond with TS as a leaving group. And then the malonate can attack this second sulfur, and we end up with a 5-membered ring, which has, of course, much less ring strain than the 4-membered ring. Well, with this 5-membered ring, we had the idea maybe we can oxidize one sulfur out to get a 4-membered ring. Is this possible? Yes, indeed, we used MCPBA, and if we used MCPBA, we could get oxidation of one sulfur. Here you see an X-ray crystal structure. And as soon as we put more MCPBA, we got indeed the extrusion of SO2 into this 4-membered ring sulfone. So SO2 next to SO2 is a very weak bond, and immediately one SO2 was expelled. Well, you've seen now a lot of chemistry with nucleophilic sulfur. What about electrophilic sulfur? So there are very crazy functionalities with sulfur. If you're interested in that, so Mike Willis, a professor in Oxford, he's a specialist in sulfur chemistry. He has nicely summarized that there are really functional groups I do not know. One of these functional groups I also did not know about 7-8 years ago was sulfinyl amines. These guys here, RNSO, NSO. You can consider them as a condensation product of an amine and SO2 minus water, right? By the way, this is the right geometry. R and oxygen are in a cis arrangement. You can easily understand that by a stereoelectronic effect, because then the lone pair here can be delocalized into the low-lying sigma star sulfur oxygen orbital. If the oxygen would be trans to this R, this wouldn't be possible. Okay, Gwindaf, a PhD student in my group, now he has finished, also tried to insert 2 heteroatoms. Gallium chloride to activate the bond as Lewis acid, and you see, well, it's possible to get these sulfinic acid amides. And you see here DR ratios. We get diastereomeric mixtures. Why do we get diastereomeric mixtures? Here is one stereocenter, and where's the other stereocenter? Of course, sulfur is a stereocenter. And here you nicely see this in an X-ray crystallography. Oxygen from sulfur, this was the major diastereomer pointing up. Also a stereoelectronic effect, because then this nitrogen lone pair can be easily delocalized here in this sigma star SO orbital. And yeah, this is the second stereocenter besides this one from the 3-membered ring. Well, we thought it would be even better to get cyclic sulfonamides and with an H at the nitrogen atom. And indeed, it was possible. There's also a reagent where you have silicon, nitrogen, sulfur, oxygen in one row. And we did this. It was inserted. Yields are a little bit worse. And then oxidation under ley conditions cleaved this very weak silicon nitrogen bond and also oxidized the sulfur further to SO2. So formally, we have now inserted here HNSO2 into our 3-membered ring systems. Okay, so far you have seen many cycloaddition reactions. But with all these cycloaddition reactions, we started from stable compounds. The cyclopropane is a stable compound, and, well, the others, thioketones, selenoketones, you can isolate, you can put to the table. So at some point we had the idea, why not using fleeting intermediates as reaction partners? So compounds which you cannot put to the bench, which have to be prepared in situ, which maybe just exist for a microsecond or a second, which are formed by other catalytic system. And we had one very special example in mind. What about using carbonyl ylides? So the idea was, okay, we use Lewis acid chemistry to activate the cyclopropane, which is a masked 1,3 dipole, as you've seen in the beginning. And then we prepare by rhodium catalysis a real 1,3 dipole, a carbonyl ylide. Well, you all know ylides from phosphorus ylides, Wittig reaction. So usually you prepare them in Wittig reactions by base and phosphonium salts, right? But of course, if you look into the structure of a phosphorus ylide, you can also think that the phosphine plus a carbene gives a phosphorus ylide, right? Lone pair, phosphine, and carbene is an electron deficient compound. So a carbonyl ylide is the same. You take a lone pair from this carbonyl group, and you form here from this diazo compound under rhodium catalysis, extrusion of N2, a carbene. And they come together, leading to a 1,3 dipole, as you see here in red. And we had the idea to react them together. So here you see again the mechanistic scheme. Rhodium expels the N2, and then you form the carbonyl ylide. The rhodium is there or is left. This depends a bit on the ring structure and on the type of conjugation, as we know. And then we have another catalytic cycle where the Lewis acid comes into play to activate the donor-acceptor cyclopropane. And here at the right side, you already see an X-ray crystal structure of the product. You see, our design worked. This is a rare case where a reaction design really worked as we thought. This was the cyclopropane carbons, and here one carbon, oxygen, carbon from the carbonyl ylide. And here you see the full story in terms of chem draws. So again, we get diastereomers. The major product is always where this orange group points axially down. This is a bit unusual. One might think that equatorial might be better, but we have here a pi star interactions between these two groups. And you see we can get 6 6-membered rings. We can also get 7 6-membered rings. Then this keto moiety forms an enol. And there the diastereomer ratios are even much better than these 5:1, 4:1. So here we only see one diastereomer. Okay, now we come to even more simple reactions, ring opening reactions. You see at the top the ring opening of donor-acceptor cyclopropanes by nucleophiles under Lewis acid catalysis. I was never really interested in that. There are many groups who do this excellently, even in an asymmetric fashion, using chiral Lewis acids. You can use amines, thiols, indoles. So we thought completely different. What about the attack of electrophiles at this position? Electrophiles attacking the electrophilic carbon of the cyclopropane. Well, this doesn't make sense, right? Why should an electrophile attack an electrophilic carbon? But we had a very special electrophile in mind. If you know what vitamin K is, so vitamin K is an important vitamin in our bodies, and it has a naphthoquinone substructure. Here you see in blue the naphthoquinone. It's a redox shuttle in our bodies, the vitamin K. So we thought we might realize this reaction. The opening by naphthoquinone of a donor-acceptor cyclopropane. You see, all atoms are there in the product, but nevertheless, how can we realize this? This is not a nucleophilic position. So the idea we had, and Alex Lücht did this, was, okay, let's take naphthoquinone. Then we give, as a gift, some electrons to naphthoquinone. Of course, now we have a very electron-rich compound here. It's a dianion. This carbon is much more nucleophilic. Well, before it's not nucleophilic. Now it's nucleophilic. This carbon might attack this electrophilic carbon. which is activated by Lewis acid. Okay, then the product is formed. This red bond is created. So what's the difference now between this substituted naphthoquinone dianion and this naphthoquinone dianion? Well, the difference is one substituent. And then let's think about your first year organic chemistry. You learned about, maybe even in school, about inductive effects. What does that mean? A positive inductive effect means the substituent pushes electron density. This means it raises the HOMO level. This means that if you have unreacted naphthoquinone, electrons might go over to the naphthoquinone, creating the dianion, while this substituted naphthoquinone dianion is oxidized to the naphthoquinone, right? And indeed, you can use a tin 2 salt. Catalytic amount is converted to a tin 4 salt, and by accident, the tin 4 salt is also the catalyst to activate this donor-acceptor cyclopropane. And here you see what we did. We used tin 2 chloride, 10 mole %, DCE 40 degrees, and we can easily open up this donor-acceptor cyclopropane. Here you see an X-ray crystal structure. Blue always the different kinds of donors of the 3-element ring. And here it also works with substituted naphthoquinones. Okay, these compounds might be not the most interesting compounds. So I told my student, okay, maybe it would be more interesting to have at least a formal insertion of the naphthoquinone into a donor-acceptor cyclopropane. So a 5-membered ring formation. So I said, okay, let's take base and do a Michael addition to the system, and then we should have this formal insertion. So he did this, and then he came back to my office and said, oh, I got a deeply red colored compound. I said, no, this is not possible. Come on. The product should be maybe yellow, maybe a bit orange, but not this compound. This color is not possible. Okay, so he measured the NMR, and you see here the NMR, 1H NMR, and you see a signal at 15. Okay, signal at 15, 1H NMR, bit unusual. And he was also able to crystallize it. Here you see the X-ray crystal structure. Completely flattened compound. Okay, only one ester group is there. OH at the pi system. This means a phenolic OH group, which mirrors this 15. And in terms of chem draws, it looks like this. So we got, by accident, by serendipity, donor-acceptor substituted fulvenes. Here you see the fulvene substructure. So a fulvene is an isomer of benzene with this exocyclic double bond and the 5-membered ring. And here you have an acceptor, and here you have a donor. And fulvus, this is based on a Latin word. It means yellow. And if you have yellow, which is donor-acceptor substituted, you shift your compound to red, or you shift your color to red. Well, here you see these structures. Yeah, so how does this work? We looked a bit into the mechanism. So this is the first reaction we designed. Electron is a catalyst. Then I said use base. Okay, this happened. And we formed this 5-membered ring. Okay, and then maybe oxidation. And I thought, okay, this is the final product. And we have evidence that this is an intermediate because we could isolate in traces and crystallize this compound. 2 esters, 5-membered ring, all carbons here, the 3 carbons are sp3. But then it's not over. So we have still base. So this hydrogen here in allylic position next to these electron withdrawing moieties, it's acidic. Okay, we can create an anion. This anion might attack this ester, leading to a carbonate, which is cleaved during workup. And then we had originally oxygen from the air, which oxidized this hydride here, leading to the fulvene substructure. Later on, we optimized this and used manganese dioxide, and then the yields were a little bit better. And then hydrolysis of the carbonate led to our products. Okay. So, so far you have seen all the time that we use Lewis acids to activate the cyclopropanes. At some point, we ask ourselves, can we also activate the cyclopropanes in a different way? Can we maybe electrochemically activate them? So the idea was, okay, let's do either an anodic oxidation, to get this radical cation, or a cathodic reduction to get a radical anion. And if you have something like this in mind, you should first measure cyclovoltammetry. And we did this for different donor-acceptor cyclopropanes, and here you see different error units. Methoxy, of course, is relatively easily oxidized, while toluol even more difficult, phenyl even a bit more, and chlorophenyl even more. But it's possible to irreversibly oxidize these compounds. So in the reductive range, we were less successful. So, okay, we thought, let's go into this direction. What kind of a reaction partner can we use? We just want to show that we can activate these cyclopropanes by electrochemistry. So we thought, okay, the best would be a reaction partner that likes positive charge and maybe that also likes radicals. So we came up with triplet oxygen. Why not doing this reaction under an atmosphere of triplet oxygen? So this is what we wanted to realize, maybe not the most important products, 1,3-bis functionalized, bis-oxidized cyclopropanes. And indeed, Simon, a really great student, then realized this. Direct anodic oxidation, HFIP as a solvent, sometimes with modulation, sometimes not, led to these hydroxy ketones. But even more interesting is the reaction mechanism. So what really happens? And there we joined forces with a group of theoretical chemistry at Braunschweig University, Christoph Jakob, and they looked into this. And they said, okay, we have a single electron transfer first, an oxidation at the anode. Then the 3-membered ring opens up. Then the spin density, as you see here on the right side, is very high at this carbon. Okay, oxygen, triplet oxygen comes into play, and we get a 5-membered ring structure. Still radical cation. And now we have a chain propagation. The missing electron is given by the starting material, while the starting material is transformed into this radical cation. And then they told us, okay, your product is this 5-membered ring, endocyclic peroxide. I said, no. Our product is this ring open product. And then they said, yeah, but this isomerization from this cyclic structure to this open chain structure has an activation barrier of 51 kilocalories per mole. Yeah, come on, this is not really accessible by room temperature. But they said, yeah, this is what we find. And then Simon, he was a very smart, but also not lazy student at all. He said, okay, I prepare also a compound with a deuterium here in this position. And he thought maybe the deuterium scrambled somehow. This was not the case, but with the deuterium, he was able to isolate this 5-membered ring. With the hydrogen here, this was completely unstable. And then I told our theory colleagues, have you looked into tunneling? And then they looked into tunneling, and indeed they found that this isomerization barrier is high, but very small and very narrow, very narrow. And this means that there is some probability of the wave function already at the other side. And of course, the probability strongly depends on the mass, and deuterium has double the mass of this hydrogen. So after some days, this was also converted into that, but we could do spectroscopy with a deuterated compound and not with a protonated one. And somehow this point of view is corroborated by the following experiments. Simon then took 4-membered rings, donor-acceptor cyclobutanes, did the same chemistry, and he was able to insert O2, getting these nice 6-membered ring endoperoxides. We could even crystallize them. Here you see a nice chair-like structure with 2 oxygens here, and they were perfectly stable. The distance from here, from this proton to this oxygen to tunnel, is much larger than in the 5-membered ring. So these are stable. Under influence of base, we could also open them up to get these gamma hydroxy ketones. Okay, my final topic, just 3 more slides. You've seen we had a lot of fun over more than a decade with donor-acceptor cyclopropanes. At some point we said, what about donor-acceptor cyclopropenes? These compounds should be even more strained, and one might think that the ring opening is even more simple, more easy, more facile. So we prepared such a donor-acceptor cyclopropene, and we thought, okay, if we can open this bond here, then we get products, and maybe we can use similar reactions than we used before, with a carbon-carbon double bond inside. Because very often, if you have the final products of donor-acceptor cyclopropane chemistry and you want to get a double bond inside the molecule, it's not possible. Because, well, if you want to oxidize this or dehydrogenate, I should say, you oxidize something else. For example, take the tetrahydrothiophene. If you take an oxidation agent, you oxidize the sulfur. So, as I just said, this strategy is usually not possible, this desaturation. So we thought, okay, let's go in with a double bond and then we get these desired products. But we prepared these compounds and it was not possible to transform them into our desired products. Just no reactivity or complete decomposition. So we thought, okay, maybe there is a surrogate for such donor-acceptor cyclopropenes. What about putting here a halide? Halide is not a great donor, but it is a donor. It has 3 lone pairs. It's at least not an acceptor. Might such structures like this be surrogates of cyclopropenes? And indeed, then we created these 3 guys, fluorinated, chlorinated, brominated. And then we used a reaction we know very well, as you see here, the reaction with thioketones. Same conditions as you've seen in the beginning. And we did this, and immediately HX was eliminated. Immediately eliminated, and we end up with these 5-membered rings, but here with a double bond. Yeah, you see the yields are great for this reaction, but okay, it's just one reaction. What about other reactions? And here you see some other reactions. Some of them you might know and you remember from the talk, I think. Here you see the insertion of 2 sulfur from this salt here, 78%, leading to this product with our modified donor-acceptor cyclopropane. This is the reaction from Jeffrey Johnson I've shown in the beginning. Insertion of an aldehyde. Works also nicely. It also works for the insertion of ketones, what usually does not work for normal donor-acceptor cyclopropanes. Here I have to confess the yield is bad, it's a poor yield, 19%, but we can also insert nitriles, leading to a carbon-nitrogen double bond. It's an unusual aza cyclopentadiene. And here you get a real cyclopentadiene if you take an enamide, and also the enamide is able to be inserted. Well, what I've shown you in the last 50 minutes are reactions with donor-acceptor cyclopropanes. So ring strain is important, but ring strain alone is not enough. So you need polarization. You need polarization to get the activation barrier down. And even the polarization, the intrinsic polarization, is often not enough. You need an additional Lewis acid to activate the system. So in the very beginning, I've shown you an iterative strategy to get oligocyclic oligoacetals and to get also 3,3 linked bispyroles. It also works for thiophenes, by the way. I did not talk about this. And then I've shown you many, many cycloaddition reactions with with thioketones, with the selenoketones. I've shown you cycloaddition reactions with fleeting intermediates, as here this carbonyl ylate. I've shown you also other ones, ring opening reactions where we used the electron as a catalyst, and then some serendipity came into play, leading to these fulvene-like structures. And finally, I've shown you how we use electrochemistry to activate the donor-acceptor cyclopropanes. And at the very end, I've shown you how we circumvented somehow donor-acceptor cyclopropanes, which were not reactive in our hands, by using a surrogate, a halide-substituted surrogate, but we could also introduce a carbon-carbon double bond by using these compounds. I do not want to stop before I have shown you where I'm from. Well, this is Germany, in the center of Europe. Here's the North Sea. This is the Baltic Sea. Poland here, Belarus, Russia, and you are here, right? So here you see the map of Germany. So Berlin, our capital. So we are in the far southwest of Germany, Freiburg. This is the city. This is already France. This is already Switzerland. It's a beautiful city at the shores of the Black Forest, famous Black Forest. It's about 1,500 meters in height. A nice skiing area in winter and hiking area in the summer. This is the view from our labs. And here you see some pictures from the city center, the old town hall. Here we have an old city gate. This is the view to the old cathedral from this mountain here. And here you see also the old cathedral. So we are very close to the old city center, but we also have new buildings. This is the modern university library, a very shiny building in the city center. So maybe the most important slide, showing the group in summer of last year. You see here, we are really close to the city center. And I'm really grateful to these people, not only for their manual contributions, but also for their intellectual contributions. I'm grateful to several funding agencies, especially the German Science Foundation and the European Research Council. I'm also thankful to several collaboration partners for X-ray crystallography and theory. And I'm very grateful that you, even under these circumstances, listen to this talk, and of course also for the invitation to give a talk at the Kharkiv Chemical Seminar via Zoom. So thank you very much.
Thank you very much for your very interesting, amazing lecture about conversion of the smallest ring to other rings or other compounds, and especially for your beautiful city. I visited Ulm, Stuttgart, Constance, but not Freiburg. Okay. I have new target for my trip and for trip of my group.
Yes.
So, dear colleagues, do you have a question?
Don't be shy.
I don't see. Okay, my question is about the first part of your lecture and the middle. The difference between these two parts is the application of catalysts. In the first part, you said it's no catalyst, it's a good, but you said that some rearrangement is impossible due to the high barrier of activation. Did you try to use catalyst to...
Oh, yeah. Maybe I did not point this out correctly. So you referred to this picture, right?
Yes, you're right.
Yeah, so these were computations just to get a feeling.
Okay.
So don't nail me down for any of these numbers. So we know oxygen donors, aldehyde acceptors, this bar here, it's a bit more than 100 kilojoule per mole. And you see here in this range and even below, there are many, many other systems. But to be honest, as you see here, well, you form with this ketone and an amine, you form the imine, but we also put acetic acid there. Yeah?
Mm-hmm.
And of course, the acetic acid protonates the imine. So this means you have some Werz catalysis for this rearrangement. So, and without the acetic acid, it was much worse, the yield, or even did not work. So catalysis is most of the time very important, either Werz catalysis or Lewis acid catalysis. But here, okay, we just said, okay, let's have a look to this rearrangement without any catalyst, because then computations become more difficult, right? And here we had 72 systems and 72 transition states and 72 starting materials and 72 products. So we wanted to have it as simple as possible, and it was already in 2011, so with less computational resources.
Okay, I understand. Thank you. Professor Garbes, please.
Hello, thank you very much. It's
Hello.
an amazing lecture. And I'm just thinking about that you use different like force and resources to make your cycles to be reagents. And this
Say it again, I did not get...
Did you try to use cyclobutane to in such type of reactions, maybe with increased donor and acceptor pairs?
So the question is whether we use cyclobutane?
Yes.
Four-membered rings?
Yes.
Yeah. So we used in some cases cyclobutanes, and I was a bit naive in the beginning. I thought all the chemistry can be done with cyclobutane as well. But this is not the case. The ring strain is a little bit less, and sometimes it's not as reactive as the cyclopropane. As you've seen in the very end where we insert this oxygen, there it worked perfectly well. But, and I show you, well, I did not put it in, but also for this compound, for this here, for example, here we could also nicely use cyclobutane to get 6-membered rings. And there are also two, 3 other reactions where we use cyclobutane, but in some cases it doesn't work.
Thank you. And another question. When you use acceptor, this is mostly carbotoxic groups. Didn't you try to use fluorine, nitro groups, and so on, other acceptors?
So, yes, this is right. We used mainly esters. We have done, I did not put the slide in, something with nitro groups. So nitro groups are, well, 2 nitro groups are too strong, and you get immediately rearrangement. 1 nitro group is usually not enough. And we used an ester in the nitro group. Maybe I show. So for example, consider here, well, if we have here, we would here have a nitro group. You see my cursor?
Yes, of course.
Yeah. So, and if you have here a nitro group and an ester, this also rearranges. And then the nitro group is inserted. This leads to a nitronate. I don't have the slide now here. Nice compound, nitronate then. So the nitro group is more easily inserted as the ester. We, and also other groups, used ketones. The problem with the ketone is that it's often too active, and you also get immediately such a rearrangement as here with the aldehyde. And then you have here an OH, or not OH, OR group. Yeah, so a ketene acetal is then formed.
Thank you. My point is that if you have extremely strong acceptors that really activate propane, maybe they will be not so extremely activate butane, and this chemistry can be like copy-paste with this butane.
Yeah, right. So of course, with a cyclobutane, maybe one should use other acceptors, but we haven't done this. So the problem is also people don't want to work with the cyclobutane because the synthesis of these cyclobutanes is very tedious. It's not straightforward. So these cyclobutanes here, the cyclopropanes are easily prepared. It's one step. Carbene insertion.
That's the reason. Thank you very much. Thank you.
Okay.
Very interesting.
Thank you. More questions, please. Okay, you several times said that strain is not enough and you need a polarization.
Yes.
But you need a polarization of stabilization of polar state. Because
so this.
Yeah, okay.
Okay, no. Ask your question, Valentin.
Because in case of stabilization, you don't need a donor acceptor. You need a delocalization of your charge, and in this case, you can use not a donor acceptor but resonance stabilization of this transition state.
Yeah, but you need a polarization first. And I have shown in the beginning this 1,3 thrid-ionic relationship, or let's say 1,3 thrid-ionic formula, but nobody has ever seen this 1,3 dipole. So it's just there to understand the chemistry more easily. Yeah, I use it to make the chemistry more easy to understand, I would say. So there is no crystal structure where you have really the cyclopropane opened and then the positive charge is stabilized by a donor and the negative charge is stabilized by the acceptor.
Okay. So, dear colleagues, I don't see any questions. Okay. Thanks again for your very interesting lecture. Here is a lecture about our beloved chemistry, pure organic. Yes. And it was very, very interesting for us. Thanks again for your time and for your inspiration of our, first of all, young scientists.
Okay, yeah, I hope the best for you. Stay safe and healthy and stay strong.
Thank you.
And I hope that the war will soon be over.
We hope the same. Yeah. Okay.
Okay. So thank you very much.
Have a nice evening.
Have a nice evening and a safe evening.
Thank you.
Bye-bye.
Bye.